Next we have some theorems and limits which you should know. Number one, as you can see, there is a limit extending to a, and there are two functions fx and gx which are being added. So in this case we can just distribute the limit to each term, like we can write this as limit extends to a f of x plus limit extends to a g of x. So we can do like this. And similarly, if two functions are getting subtracted, we can again distribute the limit as limit extends to a f of x minus limit extends to a g of x. Okay, so in number 3 what we have, limit extends to a, and here a function fx is being multiplied with a constant c. So in this case we can take out c in front of that limit, and we can write c into limit extends to a f of x. So whenever there is a constant multiplying with a function, we can take out c outside the limit. Okay, so we need not do the limit on constant. In number 4 there is a limit and the two functions are getting multiplied here. So in this case also we can distribute the limit to individual functions. So we can write limit extends to a f of x into limit extends to a g of x. So we can do like this. And similarly in number 5 we can distribute the limit as limit extends to a f of x whole divided by limit extends to a g of x. Here one thing we should note, that the denominator, that is limit extends to a g of x, should not be equal to 0. Okay, and lastly in number 6, suppose there are two functions fx and gx. Okay, and if this function is less than or equal to gx, then we can write limit extends to a f of x will also be less than or equal to limit extends to a g of x. We are doing some more theorems now. Please students, note one thing. The proof of these theorems are not that important. You can simply skip this video to the next video, okay, where we will be starting our exercises. Okay, so this proof is not important, but if you are interested in looking in this proof, so you can continue watching, or else you can skip this video to the next. There's a limit extends to a, and x to the power n minus a to the power n divided by x minus a equals to n a to the power n minus 1, where a is greater than 0. X to the power n by a to the power n divided by x minus a. Okay, so using binomial theorem, if we try to solve this expression or this function, then it will be like x to the power n minus 1 plus a into x to the power n minus 2 plus a square x to the power n minus 3 plus a cube x to the power n minus 4, and it will continue up to a to the power n minus 1, where the power of x will be 0. Okay, so now if I put a limit on both sides, then it will be limit extends to a equals to limit extends to a. Now since we know the theorem earlier, we can distribute this limit to individual term. That means limit extends to a, we can put in this term, we can put in this term. This limit can be distributed to do all the terms here. Okay, we will replace x as a here, also here, on every term. Okay, so now this will be a to the power n minus 1 plus a into a to the power n minus 2 plus a squared into a to the power n minus 3 plus a cube into a to the power n minus 4 plus up to a to the power n minus 1 to the power n minus 1 plus. Now did you see that here in this portion there is a into a to the power n minus 2 getting multiplied? So since the base are same, so the power will get added, so it will be a to the power 1 plus n minus 2, and this in third term it will be a to the power 2 plus n minus 3. Similarly here it will, so this will be equal to a to the power n minus 1 plus, now if you simplify this portion it will be plus 1 minus 2 will be minus 1, so here it will be a to the power n minus 1. Similarly in third, up till the last term is also a to the power n minus 1. See, in every term now we are getting a to the power n minus 1. Now the question is that how many a to the power n minus 1 are there? For that we will look up here, we will take the help of this expansion. Okay, so here if you notice in the first term, can I write a to the power 0 in front of it, because a to the power 0 is 1, and second term there is a to the power 1 up here. So if you notice, then there are 0 1 2 3 4 5 6 up to n minus 1. Okay, so how many total terms are there? So as you can, so you are counting from 0, okay, and you are ending up with n minus 1, so that means there are n terms. Okay, let me show some example. So if you write 0 1 2 3, so how many numbers are there? Here there are 4 numbers, because you are starting from 0, no, so that's why you have to add one more term to the last term, so 3 plus 1 is 4. So similarly here there are n number of terms. Okay, that means there are n times n to the power n minus 1, so this can be written as n times a to the power n minus 1. Hence the theorem follows. So that is, limit x tends to a, x to the power n minus a to the power n by x minus a can be written as n into a to the power n minus 1. Secondly, we have limit x tends to 0, e to the power x minus 1 by x equals to 1. Now this also I'm going to prove here, but as I said earlier, the proof is not that important. You can skip this part to next video. Okay, so let me write the left hand side portion. It is limit x tends to 0, e to the power x minus 1 by x. Okay, so now this will implies limit x tends to 0. Now here what we have to do is that this portion e to the power x, it has expansion. Okay, so its expansion is 1 plus x square by 2 factorial plus x cubed by 3 factorial plus up to infinity, okay, minus 1 whole divided by x. Limit x tends to 0. Now if I open the bracket up here, it will be 1 plus x plus, and there's a term minus 1 up here divided by x. So as you can see, we can cancel this minus 1 with this plus 1, so we will be remaining limit x tends to 0. Now as you can see in this numerator, each and every term has x, so we will take out x common. So if I take x common, it will be 1 plus x by 2 factorial plus x square by 3 factorial plus up to infinity whole divided by x. Now as you can see, the numerator x and denominator x will also get cancelled, so we will be remaining simply with limit x tends to 0, 1 plus x by 2 factorial plus x square by 3 factorial plus up to infinity. Now we will put the value of x equals to 0 in this terms. Okay, so 1 plus 0 by 2 factorial plus 0 by 3 factorial plus up to infinity, so this will finally give me 1. So hence the theorem follows. 3. Limit x tends to 0, a to the power x minus 1 divided by x equals to log of a. So for this we will start from left hand side. In left hand side we will have limit x, this will equals to limit x tends to 0. Now here expand this a to the power x. The expansion of a to the power x is 1 plus x into log a plus x square by 2 factorial log of a whole square plus up to infinity. So this portion minus 1 whole divided by x. Okay, line we will simplify the numerator. So here in numerator we will have 1 plus x log a plus x square by 2 factorial log of a whole square plus up to infinity, and there is a term minus 1 here, whole divided by x. So as you can see here, minus 1 and plus 1 gets cancels out. So here we will remain limit x tends to 0. Now if you notice the numerator here, we can see x in each and every term, so we will take out that x common. We will remaining log of a plus x by 2 factorial log of a square plus up to infinity whole divided by x. So here the numerator x and denominator out. Now this will be equal to limit x tends to 0 log of a plus x by 2 factorial log of a whole square plus up to infinity. Now as you can know that we can distribute the limit, so if I put the value of x equals to 0, then we will remain as log of a plus 0 by 2 factorial log of a whole square plus to infinity. That means here is, you see that from here everything will be 0, so only what will remain, only the first term, that is log of a, and hence proved. Next, number 4, limit x tends to 0. Now this portion I have to expand by binomial theorem. Okay, so if I expand that expression, then it will be 1 plus 1 by x into x plus 1 by x into 1 by x minus 1 divided by 2 factorial into x square plus 1 by x into 1 by x minus 1 into 1 by x minus 2 whole divided by 3 factorial to x cube up to infinity. So now if I simplify it, here I can see that this x and x get cancelled, so it will be limit x tends to 0 1 plus 1 plus, here if we simplify this whole term, then we will get 1 minus x by 2 factorial. If I simplify this term, then I will get 1 minus x into 1 minus 2x whole divided by 3 factorial plus up to infinity. Okay, now we will put the value of x as 0, then we will get 1 plus 1 plus 1 minus 0 by 2 factorial plus 1 minus 0 into 1 minus 0 by 3 factorial plus up to infinity. So it will be 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial up to infinity, and here also I can write 1 by 1 factorial. Now this is the expansion of e to the power 1, and hence the theorem follows. Number 5, we have limit x tends to 0 log of 1 plus x by x equals to 1. So here it will be limit x tends to 0. Now if I expand log of 1 plus x, then I will have x minus x squared by 2 plus x cubed by 3 minus to infinity by x. So here if I take out x common in numerator, then we will have x common 1 minus x by 2 plus x by 3, sorry, x squared by 3 minus up to infinity by x. So here x and x get cancelled. Limit x tends to 0 1 minus x by 2 plus x squared by 3 minus up to infinity. Now if I put the value of x, then this portion will be 0, this portion will be 0, everything will be 0 except the first term 1, so it will be equals to 1, and hence the theorem follows.